Hello everybody, it's Mrs. Pound and we are studying Chapter 11 on Chemical Calculations from BGU Chemistry's 5th edition. Today we're going to talk about Section 11.2 on stoichiometry. Say that with me, stoichiometry. So our objectives today will be to outline the process for performing stoichiometric calculations and to predict the theoretical quantities of substances involved in chemical reactions. So stoichiometry is the measurement and calculation of the mass and molar relationships between reactants and products in chemical reactions. When we do stoichiometry, we must work with equations that are balanced. So we're going to be using this equation throughout our whole discussion. The reaction of phosphorus with oxygen to produce phosphorus oxide. So what we notice from this reaction is these numbers in front, the coefficients make ratios. And remember, the coefficients out front are going to stand for moles. So we know that 1 mole of phosphorus reacts to form 2 moles of phosphorus oxide. So their ratio is 1 to 2. We can also see from the equation that 1 mole of phosphorus reacts with 5 moles of oxygen gas, and a ratio of 1 to 5. And 5 moles of oxygen reacts to form 2 moles of phosphorus oxide, so their ratio is 5 to 2. Now these ratios are called mole ratios. This is the ratio between the moles of one substance and the moles of another substance as indicated by the coefficients in the balanced equation, and these are really important. These are used as conversion factors to convert from moles of one substance to moles of another. Sometimes we refer to these as a coefficient bridge. So let's talk about converting moles to moles. Let's see how we would do that using our balanced equation and these molar bridges, these coefficient bridges. So a problem we might encounter is a chemist wants to produce 25 moles of phosphorus oxide. How many moles of phosphorus must be burned? So in any problem like this, we start with the number that they give us, 25 moles of phosphorus oxide. We then go to our equation for the mole ratio. And we want to get to phosphorus. So we see that the ratio is 2 moles of phosphorus oxide because it has a 2 in front of it to 1 mole of phosphorus because there is nothing in front of it, so it's understood to be a 1. So we make the ratio so that our moles of phosphorus oxide cancel out. And then when we do the math, we divide 25 by 2, we find that 12.5 moles of phosphorus are required for that reaction. Another question might be, how many moles of oxygen were consumed by the reaction? So we know that we started out with 25 moles of phosphorus oxide. When we look at our equation, we know that 2 moles of phosphorus oxide are produced, and in order to produce 2 moles, we need 5 moles of oxygen. So we use this mole ratio. So we put phosphorus oxide on the bottom, oxygen on the top, so that the phosphorus oxide cancels out. And we find that it is 62.5 moles of oxygen are required to produce 25 moles of phosphorus oxide. Now, there's another way to do this problem because we also calculated previously that 12.5 moles of phosphorus are required. So if we use that number, we see that we use our mole ratio of 1 mole of phosphorus to 5 moles of oxygen in the reaction. And we also can calculate 62.5 moles of oxygen. So there are often more than one way to do one of these problems. So now let's look to a mass to moles problem. So a question might be, how many moles of phosphorus oxide are produced by burning 1.55 kilograms of phosphorus. So for this problem, we must first find the molar mass of phosphorus. And so if we look at our periodic table, phosphorus is right here, 30.97376. So I'm just going to round that off a bit. So 4 times 30.97 grams equals 123.9 grams of phosphorus, P4. So we take and we write down how many moles, the number of moles from the problem. Okay, so so we write down the quantity from the problem, 1.55 kilograms of phosphorus, but our molar mass is in grams. So the first thing we have to do is we have to convert from kilograms to grams. So we know that 1 kilogram contains 1,000 grams. Then we put our molar mass in there. Our molar mass goes on the bottom because the grams of phosphorus have to cancel out, and we have 1 mole of phosphorus is 123.9 grams of phosphorus. We can then see that we use our molar ratio, 1 mole of phosphorus to 2 moles of phosphorus oxide from our equation, and we calculate that it is 25 moles of phosphorus oxide that will be produced from 1.55 kilograms of phosphorus when it is burned. So finally, so another type of problem we can do is mass to mass. So using the same equation, we must calculate the molar masses of the known and the unknown substances when we do this. So we already know the phosphorus. We need to know the oxygen, so 15.9994. So the question is, what mass of oxygen will react with 1,239 grams of phosphorus? We already know the molar mass of phosphorus, so I just copied that down. Oxygen, the molar mass is 2 times 16.00 grams. I just rounded it off, is 32.00 grams of oxygen. So we write down our amount of phosphorus. We then have to convert to moles. So we know the molar mass of phosphorus. Whenever we're going from one substance to another, we have to go through moles, okay? So you always convert to moles. So 123.9 grams of phosphorus goes on the bottom, 1 mole of phosphorus on the top. So we're converting it to moles in that step. Then we use our mole ratio. So 1 mole of phosphorus goes on the bottom, so it will cancel the 5 moles of oxygen on the top. Then we have to have the molar mass of the oxygen. So 1 mole of oxygen goes on the bottom, 32.00 grams of oxygen on the top for the molar mass. I call this a molar mass sandwich because you have, molar mass on one side, mole ratio in the middle, molar mass on the other side. So I call this a molar mass sandwich. The molar mass is the bread and the mole ratio is the filling. And when we multiply across the top and divide by what's on the bottom, we get 1,600 grams of oxygen will react with the phosphorus. And finally, another type of problem we can do is number of particles. So here we have our same equation, and our question is how many oxygen molecules will react with 1,239 grams of phosphorus. So we start again with our 1,239 grams of phosphorus. We always have to go through a mole. So we take and we convert to the molar mass. Using the molar mass, we convert to moles. So we divide by 123.9 grams of phosphorus. That goes on the bottom. 1 mole of phosphorus goes on the top. Then we have to use our mole ratio so that we can get to oxygen. So we see that 1 mole of phosphorus reacts with 5 moles of oxygen. Moles of phosphorus goes on the bottom, so it will cancel. And then finally, we can use Avogadro's number for the number of molecules, and we know that 1 mole of oxygen contains 6.022 times 10 to the 23rd molecules of oxygen gas. So when we multiply across the top and divide by what's on the bottom, we get 3.011 times 10 to the 23rd molecules of oxygen. So our objectives for today's video were to outline the process for performing stoichiometric calculations and to predict the theoretical quantities of substances involved in chemical reactions. So don't forget your 5 questions in your notes, and I'll be back with another video.